Enumeration, Wikipedia audio. An enumeration is a complete, ordered listing of all the items in a collection. The term is commonly used in mathematics and computer science to refer to a listing of all of the elements of a set. The precise requirements for an enumeration depend on the discipline of study and the context of a given problem. Some sets can be enumerated by means of a natural ordering, but in other cases it may be necessary to impose a ordering. In some contexts, such as enumerative combinatorics, the term enumeration is used more in the sense of counting with emphasis on determination of the number of elements that a set contains, rather than the production of an explicit listing of those elements. In combinatorics, enumeration means counting, i.e., determining the exact number of elements of finite sets, usually grouped into infinite families, such as the family of sets each consisting of all permutations of some finite set. There are flourishing sub-areas in many branches of mathematics concerned with enumerating in this sense objects of special kinds. For instance, in partition enumeration and graph enumeration, the objective is to count partitions or graphs that meet certain conditions. Enumeration in combinatorics. In set theory, the notion of enumeration has a broader sense, and does not require the set being enumerated to be finite. When an enumeration is used in an ordered list context, we impose some sort of ordering structure requirement on the index set. While we can make the requirements on the ordering quite lax in order to allow for great generality, the most natural and common prerequisite is that the index set be well ordered. According to this characterization, an ordered enumeration is defined to be a surjection with a well-ordered domain. This definition is natural in the sense that a given well-ordering on the index set provides a unique way to list the next element given a partial enumeration. As a surjective mapping from N to S. This definition is especially suitable to questions of computability and elementary set theory. The most common use of enumeration in set theory occurs in the context where infinite sets are separated into those that are countable and those that are not. In this case, an enumeration is merely an enumeration with domain omega, the ordinal of the natural numbers. This definition can also be stated as follows. We may also define it differently when working with finite sets. In this case, an enumeration may be defined as follows. In the first definition, it varies whether the mapping is also required to be injective, and / or allowed to be partial. In some applications, these differences are of little importance, because one is concerned only with the mere existence of some enumeration, and an enumeration according to a liberal definition will generally imply that enumerations satisfying stricter requirements also exist. Enumeration of finite sets obviously requires that either non-injectivity or partiality is accepted, and in contexts where finite sets may appear, one or both of these are inevitably present. F, N, Z, / math, is a bijection since every natural number corresponds to exactly one integer. The following table gives the first few values of this enumeration. As a bijective mapping from S to an initial segment of the natural numbers. This definition is especially suitable to combinatorial questions and finite sets, then the initial segment is for some n which is the cardinality of S. In set theory, there is a more general notion of an enumeration than the characterization requiring the domain of the listing function to be an initial segment of the natural numbers where the domain of the enumerating function can assume any ordinal. Under this definition, an enumeration of a set S is any surjection from an ordinal alpha onto S. The more restrictive version of enumeration mentioned before is the special case where alpha is a finite ordinal or the first limit ordinal omega. This more generalized version extends the aforementioned definition to encompass transfinite listings. Under this definition, the first uncountable ordinal, omega, 1, can be enumerated by the identity function on, omega, 1, so that these two notions do not coincide. More generally, it is a theorem of ZF that any well-ordered set can be enumerated under this characterization so that it coincides up to relabeling with the generalized listing enumeration. If one also assumes the axiom of choice, then all sets can be enumerated so that it coincides up to relabeling with the most general form of enumerations. Enumeration in set theory. Since set theorists work with infinite sets of arbitrarily large cardinalities, the default definition among this group of mathematicians of an enumeration of a set tends to be any arbitrary alpha sequence exactly listing all of its elements. Indeed, in Jeck's book, which is a common reference for set theorists, an enumeration is defined to be exactly this. Therefore, in order to avoid ambiguity, one may use the term finitely enumerable or denumerable to denote one of the corresponding types of distinguished countable enumerations. Formally, the most inclusive definition of an enumeration of a set S is any surjection from an arbitrary index set I onto S. In this broad context, every set S can be trivially enumerated by the identity function from S onto itself. If one does not assume the axiom of choice or one of its variants, S need not have any well-ordering. Even if one does assume the axiom of choice, S need not have any natural well-ordering. This general definition therefore lends itself to a counting notion where we are interested in how many rather than in what order. In practice, this broad meaning of enumeration is often used to compare the relative sizes or cardinalities of different sets. If one works in Zermelo-Fraenkel set theory without the axiom of choice, one may want to impose the additional restriction that an enumeration must also be injective, since in this theory, the existence of a surjection from I onto S need not imply the existence of an injection from S into I. In computability theory, one often considers countable enumerations with the added requirement that the mapping from N to the enumerated set must be computable. The set being enumerated is then called recursively enumerable, referring to the use of recursion theory in formalizations of what it means for the map to be computable. In this sense, a subset of the natural numbers is computably enumerable if it is the range of a computable function. In this context, enumerable may be used to mean computably enumerable. However, these definitions characterize distinct classes, since there are uncountably many subsets of the natural numbers that can be enumerated by an arbitrary function with domain omega and only countably many computable functions. A specific example of a set with an enumeration but not a computable enumeration is the complement of the halting set. Furthermore, this characterization illustrates a place where the ordering of the listing is important. There exists a computable enumeration of the halting set, but not one that lists the elements in an increasing ordering. If there were one, then the halting set would be decidable, which is provably false. In general, being recursively enumerable is a weaker condition than being a decidable set. Enumeration as listing. Enumeration in countable versus uncountable context. Examples. Properties. Ordinal enumeration. Enumeration as comparison of cardinalities. Enumeration in computability theory.